Film is a very straightforward technology. It just involves taking a two-dimensional image and focusing it onto a two-dimensional piece of film, and there you have a photo. But video, and by that I mean moving electronic images, has a very different history with a lot of changes that have really transformed the way it works. This video was sponsored by B&H-Photo, which is kind of fitting because that's where I get a lot of my gear to make these videos. So I'll tell you more about them later, but now it's off to San Francisco. I'm going to meet with a guy who knows a lot about old video gear, and he's got some he's going to show me. Richard, nice to meet you.
Nice to meet you, Derek. Come on in.
Okay.
So welcome to Lab Guy's World.
It's a cool spot you got here.
Thank you.
The fundamental problem of video is taking this two-dimensional light image and turning it into a one-dimensional electrical signal. So how do you do that? Well, the solution actually comes from the first ever fax machine, which, believe it or not, was invented in 1843 by Alexander Bain. Now, he was a clockmaker. His invention involved a transmitter and receiver, which each had a pendulum, and those pendulums were synchronized. So what would happen is, at the transmitter, there would be a metal sheet on which something was written or drawn using a non-conducting ink.
So a finger at the transmitter, an electric finger, would stroke over the paper, and wherever there was iron, it would conduct. And that conducting signal was sent to the other end, which was applied to paper with a chemical that would turn dark when electricity flowed through it. And it would reproduce a very accurate image of the handwritten note you just made.
Now, Alexander Bain only ever transmitted static images, but some people have called him the real father of television, because he invented scanning. This idea of moving back and forth across an image, breaking it down into lines. But if you really want to get moving images, well, you need to be able to scan much faster. So we have to jump forward to 1884, and a 23-year-old German university student named Paul Nipkow. He patented what is called the Nipkow disk, which is basically a big disk with a spiral of holes in it.
The inner pinholes do the scanning. And if I go fast enough, you can see the scanning.
You would put a light behind this Nipkow disk, and so you'd have a spot of light which scans across your subject, say a person. And then there would be reflected light off that person, which would be picked up by some light sensors. That would create an electrical signal which you could transmit over distance to a receiver. Now, at the receiver, you use that electrical signal to modulate the brightness of a light source. And then in front of that, you place a synchronized Nipkow disk. And so the result is a recreation of the image from the transmitter.
So it was just barely at the limits of the ability to make a viewable picture, and it was actually broadcast for a couple of years in Britain, and in America and other countries did experimental broadcasts using this technique.
This is arguably the first ever broadcast television image. It was broadcast for a few hours a day for several years, and it was used by engineers to perform experiments and try to improve the quality of the broadcast.
What it proved was that this wasn't the way to do it.
So by 1939, mechanical TV was all but phased out, and it was replaced by all-electric TV. Specifically, the cathode-ray tube. So this is a glass vacuum tube with an electron gun at the back, and the electron gun would fire a beam of electrons at the screen where it was coated in a chemical which produces light when it got hit by the electrons. That's called a phosphor. And using magnetic fields, this beam was scanned across the screen, top to bottom, left to right, and you would vary the brightness of the beam by varying the voltage on a control electrode, essentially determining how many electrons would get sent out in that beam at any instant to hit the screen. So if you send out a lot of electrons, you get a bright spot. If you don't, then you get a dark spot. And in that way, you can produce a nice black and white image. And if you're wondering about color TV, well, there were a number of dead ends along the path to the red, green, blue pixel system that became the standard. Like this TV with a spinning color wheel.
I named the project Goldmark 1 in honor of Dr. Goldmark. The television part is a standard black and white picture tube.
It displayed 24 frames per second, but each frame required 6 scans, blue, green, red, blue, green, red. It worked really well, but it wasn't backwards compatible with black and white TVs.
So the green tube
And this
shines
is a
straight
mini
through.
trinoscope, so named for
blue
its
tube
3
comes in this
cathode
way,
ray
and
tubes, one for
it's
each
the
color,
blue mirror,
and their
blue
images were
reflecting mirror.
combined
All of
with
it.
prisms.
The downside of a trinoscope monitor is that for every inch you add diagonally to your screen, the volume of the cabinet increases by like the power of something like 3.5. They get huge fast.
So the ultimate solution was to have red, green, and blue phosphors for each pixel and 3 electron guns to determine their relative brightness. Now the number of lines those electron beams make across the screen is in theory 525 every 30th of a second. But this is achieved by scanning every other line each 60th of a second. So it actually takes 2 scans to make 1 frame. This is called interlacing. And what you'll notice watching this is that most of the time you're actually staring at a blank screen. The illusion of a continuous moving image is made possible by our persistence of vision. That is, we don't stop seeing something instantaneously after light stops entering our eyes. So initially I was thinking this wouldn't be too hard to film. I mean, a 30th of a second or a 60th of a second, that's not terribly fast. But then if you think about it, 262.5 lines being drawn every 60th of a second, that is 15,750 lines drawn per second. That is fast. So if you want to be able to see the lines being drawn on, you need to shoot faster than 15,000 frames per second. A lot faster, really, to be able to see this clearly. And so I am using the Phantom V2512. That is the beast that is allowing me to produce these images. Now the actual resolution of these TVs turned out to be around 480 lines. So when you select 480p on YouTube, that's why this is an option. And I guess it's worth pointing out that the tube in YouTube is this thing, a cathode ray tube. So in the time before light-sensitive chips like we all use in our cameras today, how did you actually create the image to display on a television? Well, there were many vacuum tube designs. One of the most common was the image orthicon tube, sometimes called IMI for short. In fact, that's where the name EMIs comes from. So the way it would work is you use the camera lens to focus an image onto the front of the image orthicon tube. And that was coated with a photoelectric substance, so it would release electrons in proportion to the light that hit them. Now those electrons were collimated by magnetic fields and sent straight back, so essentially you had an electron version of the image sent straight back to a target, which was a very, very thin glass plate. And of course, where there's more electrons, that creates a more negative spot on this target. From the back of the tube, you'd send forward an electron beam to scan across the target. And so these electrons, as they came in, the more negative a spot that was on the target, the more that beam would get reflected. And so that reflected beam was amplified in the tube and then used as the signal to essentially determine how bright that part of the image should be. So this is how television images were created and displayed for decades. But here is the crazy thing. There was no way to record them. I mean, the purpose of video or the purpose of electronic images was really to transmit something from one place to another. Television literally means seeing at a distance. It's not about recording for replaying later, as film was. The thing that blew me away was realizing that video cameras existed for a couple decades before videotape.
That's right. That was the era of live broadcasting.
But this introduced some problems. For example, in North America, in the US, a lot of the TV programs were produced out in New York. And there was a coaxial cable which went across the whole of the US, and that could deliver programming to, say, Los Angeles. But it was at the wrong time. I mean, a news broadcast from New York at 6 or 7 p.m. couldn't just be broadcast live at 3 or 4 p.m. on the West Coast. It just didn't make any sense. So you needed to time delay it. So how did they do it? Well, the answer was to take a film camera, a cinema camera, and point it at a television screen and actually film the television screen. Then you would quickly develop the film and bring it back 3 hours later to broadcast it live, to scan it in and broadcast that film as though it were live.
But now, when I bring it back to the TV studio and stick it into the telecine, the picture doesn't look right. The lines aren't lining up right. And besides, you're trying to sample two sets of lines back together and they don't.
This became such a prevalent method of doing business for the TV networks that by 1954, the television networks, to time delay their programming, were using more film than all the film studios in Hollywood combined. This is absurd and expensive and wasteful. So a different method was really needed. And that came along in 1956 with the invention of the first workable videotape recorder. It was the size of a large desk and it cost a fortune. It ran on this 2-inch magnetic tape with little video heads spinning at 14,000 RPM. We're talking as fast as a jet engine. That is the kind of technology it took before video became what we kind of know it as today, a method of recording and storing images rather than a way of just transmitting vision from one place to another. But we've come a long way since then, miniaturizing the tapes down into VHS and beta, and eventually down to DV and mini DV, and now we are on to solid state storage. And I know I've glossed over a lot of the history here, but now we're in a situation where video is better than film. You can see that in 2012, that was the inflection point between people using film to shoot the top grossing movies, changing over to people using digital. And what this has done for people like you and me is it's made it possible to make really good images. And the question I have is, what does this do to a society? What might it do when people can share every part of their lives with video? This part of this video was sponsored by B&H Photo, literally one of my favorite stores in the world. They have all the greatest and newest camera gear, plus pro audio and lighting and computers, basically anything you could need to make high quality video. And every time I'm out in New York, I go and visit the store. The last time I was there, I asked them for a gimbal because I'd been seeing all these comments saying my videos were too shaky. And so they recommended this one right here, and I've really loved it. It's so smooth, I can hold it with one hand. It is pretty lightweight, and it's just been great, and I think it's really improved the quality of my videos. And when I'm back here in LA, I still shop with them online because there is no shop like that in LA. In fact, this camera, the Sony a7R III, I'd highly recommend it. I bought it for my wife for Christmas, the Christmas before last, and it was back ordered, but you can actually sign up through their website to get notified when it's in stock, and I did that and managed to get it in time for Christmas. So it's a really great shopping experience. The people are so knowledgeable. It's a mom and pop shop. It's got anything you could ever want. I highly recommend you check out B&H Photo. I'll put a link to them in the description. And thanks to B&H for sponsoring this video.